Today we're looking at a programming problem where we need to find the middle node of a linked list. May sound easy enough, but we've got a couple of constraints that will invalidate maybe the more obvious approaches. The first constraint is we have to find the middle node in one pass of the linked list. That is, we can't traverse from the start of the linked list down to the end and then go back and retraverse. We have to find it in one pass. Secondly, we need to find the middle node while using constant space. That means we're unlikely to be able to use any fancy data structures that Java provides. The solution turns out to be quite elegant once you understand the trick. So let's get started. So our problem today is again courtesy of firecode.io. So we've got a singly linked list here, and we're permitted one pass of the linked list to find the middle node. We can always assume that the head of the list is defined, so we don't have to check for nulls. And we need to shoot for constant space complexity. So looking at some examples, if we just have a single node in the linked list, we can return that node. If we have two nodes in the linked list, we would return the second node, I guess because there is no middle node in the linked list because it's an even length. We would return the node immediately to the right of where the middle would be. If we have 4 items in the linked list, like this, we would return that node right there. Again, it's even length. We don't have a middle. So we return to the node immediately to the right of where the middle would be. And finally, our last example is when we have 5 elements in the list, we return the middle node, which is the 3 here. So as defined, this is going to be a linear time algorithm because we're only allowed one pass of the linked list. And they want us to shoot for constant space complexity. So let's head to the whiteboard and sketch out a solution. So suppose this is our linked list. We've got some nodes in the linked list, each storing some data values. And we're given a reference to the head node of the linked list. So with a linked list, when we're given a reference to the head node, we have no idea how long the linked list is. Could be 5 elements long, could be 10, could be 1,000,000. So one approach to solve the problem might be, well, let's simply count the number of nodes in the list. So we could traverse the list, keeping track of how many nodes we've visited. At the end, we'll know we visited, in this case, 1, 2, 3, 4, 5, 6, 7. So we know the list is 7 nodes long. Then we could go back to the start and traverse to find the middle node. However, the problem says we have to find the middle of the linked list in one pass. So we're not allowed to go back to the start and retraverse half the list to find the middle node once we know how long it is. So that solution is out. Another solution might be, well, if the linked list were in some other format or some other data structure, we could just access the middle element directly. So for example, if this linked list were instead in an array, with Java arrays, we know how long the array is, so we could just immediately access the middle node. So one approach might be, well, traverse the list, adding each element to an array or an array list. Once we get to the end, we know how many elements there are, and we can just simply access the middle element of the array or the array list. Unfortunately, we have to shoot for constant space complexity for our solution. And this proposed solution uses linear space complexity because the amount of space that we're going to use up in the array or the array list that we create is directly proportional to the number of elements in the linked list. So that's no good. We can't have our data structure growing in accordance with how long the linked list is. So the trick then is we need to figure out how to traverse down to the end of the linked list and at the same time kind of remember where the middle is. So how we do that is by actually having 2 references to elements in the linked list. This top reference here, we'll call this the lead, which is going to go out front, and we'll call the bottom reference here the lag, which is going to lag behind. And what we're going to do is advance this lead reference 2 nodes at a time down the linked list, while the lag reference here only advances once. So they both start on the head node. This lead reference is going to go here, jump 2 nodes. This lag reference is only going to jump 1 node and then stop. Then we're going to do the same thing again. The lead reference is going to jump 2 and then stop. The lag reference here is going to jump 1 and then stop. So you can see what's happening is this lead reference is jumping 2 nodes at a time. The lag reference is jumping 1 node at a time. So this lead reference will be twice as far down the linked list as what the slower the lag reference is here. So by the time this guy gets to the end of the linked list, and we advance this one, the lag reference here is going to be in the middle because it's gone half as far as the lead reference, which has made it to the end of the linked list. So this lag reference will be a reference to the middle node in the list. So let's look at a couple more test cases just to make sure our algorithm is going to work. So let's look at the case when the linked list is only 1 node long. So in that case, our lead and lag indicators both start at the head node as usual. And we won't be able to advance anymore. So we'll have to stop because we've reached the end of the list. So we would return just this element, which is the middle element. So that would be fine. Let's have a look at this one here. So our lead indicator jumps by 2 and then stops. Our lag indicator just jumps by 1 and then stops. Again, our lead indicator jumps by 2. And you can see we've overshot the list here. It's okay. Our lag indicator would jump by 1 and then stop. So in this case, we've overshot the end of the list. It happens to be because the list is of even length. But our lag indicator is still pointing on the middle element that we want to return, so that works. So we'll have to stop our loop when either we get to the last element or we overshoot the last element by 1. In either case, we know that our lag indicator here is going to be pointing at the middle node. So let's have a look at the solution in Java. So for our implementation, we just have the 2 references, that they both lag and lead. They both start at the head node, and we want a loop. And our while condition, as we mentioned, is while our lead element is not null, our lead element will be null once it overshoots the end of the list. So we want to continue while the lead is not null and the lead.next is not null. So this is what happens when the linked list is of odd length and the lead actually lands on the final element of the list. So while those 2 things are true, we just simply move the lag reference to the next element, and we move the lead reference 2 elements ahead. So lead.next. And this is safe because we know that lead.next is not equal to null. So we continue doing that until either the lead indicator overshoots the end of the list or lands exactly on the end of the list. In either case, our lag reference will be the middle node of the list. So for the time complexity of the algorithm, advancing the lead reference 2 at a time until it gets to the end of the linked list. So we're going to go through the loop 1/2 n times, where n is the number of elements in the list. So we've achieved our linear time algorithm. And similarly, we're only doing 1 pass because we go to the end of the list and stop. Space complexity-wise, all we have are just 2 references to nodes in our list that get updated every time. The space used by our algorithm is constant and doesn't grow in relation to the size of the list. So we've achieved our constant space complexity. Submitting our solution. It's like all tests passed, so we're good. Thanks for joining me today. Hope you found this useful. We'll see you next time.